Okay, hi everyone. I'm Yaron. I'm a co-founder and CTO for Iguazio, an MLOps platform company. And what I'm going to talk today about in my session is about how to migrate. Everyone knows AutoML is a mechanism to automate the process of building models. What we're going to speak about is AutoMLOps, is how do we automate the way we deploy models and machine learning applications into production. So before we dive into the content of the presentation, what's the real challenge that most organizations are facing? It's essentially the ability to move from research development environments where you build models based on some sample data into a full-blown application running in production, always on, that feeds off real live data and essentially fuels real application. And MLOps is essentially sort of the bridge between this research to production. And what we want to have is more and more automation to essentially help us within this journey. So, what does it really mean? What do we do today, and what should we do in order to ease that pain? So, today, most of our organization, when they look at the machine learning problem, they look at this slide as essentially this is the challenge we're trying to solve. There's a data science team that gets some data from a data warehouse, from a data lake, from some CSV or Excel spreadsheets, working on their notebooks or IDs, and preparing the data, analyzing the data, and then sort of running training, whether it's using an online service for training or AutoML, or writing their own custom code and then evaluating their server loop, and eventually they generate a machine learning model in an interactive way and throwing that model into a container or an endpoint or deploy that. So this is the usual ritual, very interactive by nature, a very iterative process. But when we go into real world live production environments where machine learning is deployed, we need something that looks more like this. Essentially, the data is not just Excel spreadsheet. The data is live. It's arriving from live endpoints, from streaming data, from operational databases, and so on. And we don't train the models interactively. We want to retrain the models automatically every time we change the data, every time there is a drift, every time the code changes, and we need to add a feature. So we need more of an automated pipeline for that. And finally, we also need to build online serving pipelines. It's not just about serving a model, it's also about intercepting a message with an API, enriching data, serving a model, driving some action, and you need to monitor all of that. So this is essentially the end in mind. But still, most organizations are still sort of living in that space, and they think this is MLOps. So if this is MLOps, what do we really need in that space? We need a way to track everything we're running and compare experiments, etc. So there are many tools in the market or open source packages like MLflow, weights and biases, and others that allow you to record every time you run a job. You can record the output and you can track your experiments. And today you'll see more and more technologies around what is referred to as auto logging. Essentially, when you're running your experiments, you can automatically grab the different matrix and artifacts from your experiment and be able to compare them. But this is not solving the real problem that we just discussed, because the real problem is how to build all of that stuff. And all of that stuff is really not just about tracking the experiments, it's about recording all the information, data lineage, producing artifacts, scaling the workloads from something small to something very, very big, addressing security, addressing many other operational aspects. So we need to advance from some logging of experiments or AutoML, which is automating machine learning, to try and automate all the different processes that people do in order to produce machine learning workloads or data engineering workloads into production. So if we're looking into this example of tracking experiments where the key goal was visualization or collecting data for reproducibility, we want to add a lot more things into automation. For example, we want to auto-tune our models. So when we write the code, we want some automation thing to run various experiments and various permutations and choose the best model for us. And that could be by automatically injecting parameters, collecting the results, and trying to optimize this problem. We may want to not only log results or the matrix, we may want to address other aspects of legal and governance and explainability of our model. So that requires other things like recording a lot more metadata when we're running all those things, and not just recording that in an interactive flow as we've seen before, that the main purpose is visualization, essentially recording all of that data and putting it in a database, even when we're doing everything automated, even when we're running a fully automated retraining flow every few days, we need this retraining flow to record a lot of metadata, like lineage of the data, what were the outcomes, what was the code, what was the code version, or the Git commit used in that, with what kind of packages, who ran the execution, who approved the process, and so on. So there's a lot of other data that we may want to record. We want to be able to simplify pipelines, because usually we don't just launch a training job. We need the data preparation, followed by training, followed by some testing, followed by potentially optimization of our model, and a few other steps, and maybe in some cases multi-stage of combining multiple models into a single application. So we also need to think about how do we compose something and record something and automate something that's not a single step or individual step like training, but essentially is a flow of multiple stages. And beyond that, training is very expensive, especially if you're trying to do that on lots of data, or you have a complex model, or you're trying to evaluate many different permutations of your parameters. So you need to be able to profile your workloads, the CPU usage, the GPU usage. Maybe you can optimize something in your code in order to reduce the overall cost of your computation. Maybe even optimize your code to run in a better way, or scale your code automatically without having to write additional logic. So this is an example. And also, when we want to move from development to production, there's a certain amount of metadata that we need to collect, and we don't want to do that manually. I'll give you an example. If we want to monitor drift of a model, we have to be able to collect a lot of statistical attributes of the training data set. So later on, when we're running in production and we monitor our models, we need to compare the data set in training and its statistical features with the statistical features generated by the real-time serving monitoring engines. And this requires storing some metadata about the training and comparing it with the data of serving. So this is something, if you're not going to do it automatically, you'll need to do it manually. So the thing about recording everything that goes in and out, or automating the flow of execution, is illustrated in this diagram. So essentially, I have some code. This code usually runs within an environment that has some extra packages, Conda, pip, etc., maybe some frameworks. All of that is running within an operating system, certain Python, certain Linux, maybe other aspects of the operating system. And this is all running on top of resources, whether these are GPUs and CPUs, etc. We want to record all of those. But also everything that we're executing, we want to be able to record or inject the different parameters, which could be, just some simple parameters of our job. Maybe some, we want to be able to push credentials, because our job is accessing some external data resources or some protected assets. We want to be able to push data into it, and maybe we want to also add a bunch of labels. So when we're running something, we can label it and later on compare different runs with the same labels and so on. So these are the things that go into a workload, and then we have the stuff that goes out of a workload, which are a variety of numeric results, charts, artifacts of different sorts, operational data like logging, monitoring, matrix, CPU, GPU, memory usage, and data. So this is essentially how we abstract away the computation. And what we can do is essentially record everything that goes in, record everything that goes out. But beyond that, we can even automate. We can even start pushing a variety of parameters here, evaluate the results, and let this thing auto-optimize itself for picking the best model, just as an example. Now, another thing that I mentioned is that in many cases, if you look at a pipeline, it's multi-stage, like you're doing some data preparation and then training and so on. So we also need to be able to pass data along the pipelines from one step to another. So the ability to essentially chain those functions and chain the inputs and outputs is also very important. But in order to do that integration, we need a common layer of metadata. We need sort of a common language for those components to talk to each other. And we need to be able to automatically monitor and log all those results. Okay, so this is another point. Another aspect beyond just tracking the experiment, the problem is all of those things that we just talked about require additional code. So this is just an example from MLflow. In order to log all of those different metrics, I need to add code that logs all those different metrics and parameters and maybe results and data assets and data sets and so on. In order to accept variety of parameters, I need to start doing arc parsing to my job. I'm putting command line parameters, and this is heavy duty stuff. It's tedious. But even beyond that stuff, we want to integrate all those things into a CI/CD flow. So how do we integrate that into a CI flow in the simplest and easiest way, and into reporting systems that will be able to take all of that data and push it into systems that will track governance or compliance and so on. All that stuff is nice for a single container. What happens if we want to distribute our workloads across multiple virtual machines? So we need a way to distribute the workload. And just as an example, if we're running this job on a container somewhere in the cloud and it needs to get access to data, we also need to start integrating with all the data APIs. If you're in Amazon, you need to integrate with Boto. If you're in Google, they have their own libraries, or Amazon or Azure, and so on. And if you're working locally for debugging, you work with your own file system to just work out with files. So now you're starting to need to do all this glue logic, and so on. So there are many different manual steps that usually is not done by the data scientist. In many cases, it's the machine learning engineer or a data engineer that starts, or DevOps people that take the piece of code that was generated in the notebook by the data scientist and start adding operational considerations, scaling, security, logging, and so on. So that's a lot of work. So we came with some open source projects that they're all about automating all that flow. So there are two main open source projects that I'm going to discuss. One is Nucleo as a serverless engine. Is essentially an engine that you throw some code at it, and it knows how to turn it automatically into a fully elastic microservice. And the other one is MLRun. It's a machine learning orchestration or MLOps orchestration framework that has a lot of components that we're going to discuss. And those are essentially trying to automate all those different things that we are seeing here. So what is MLRun? Essentially, if you think about it, it has 4 individual components. They're all running on those serverless functions that I'm going to discuss in a minute. The first part is the feature engineering aspect. It has a very powerful feature store for online processing and offline processing, which essentially knows how to connect to a variety of data sources, run transformation pipelines, catalog features, and serve them in real time or batch. The other aspect of MLRun is all the automation around building machine learning CI/CDs, essentially leveraging those serverless functions on one end and integrating with a variety of CI/CD frameworks like GitHub, Jenkins, and so on to extend them to become sort of an MLOps automation. The third step is building those real-time pipelines automatically by leveraging the artifacts and models and things that were generated in the CI, machine learning CI flow, and turning them into real-time pipelines that are, you can do rolling upgrades, auto-scaling, and so on. And the last piece is essentially collecting all the data from those assets and doing real-time analytics to identify data violations and drifts and accuracy problems and so on, and also record all the production data back into the system so you can do retraining logic and redeploying models which are fresh and so on. So this is in general the architecture of MLRun with those 4 components, and it integrates seamlessly with the other components of the stack through an API. Essentially, you can have integration with various BI and data exploration tools with different IDs, AutoML training frameworks, CI frameworks, which I mentioned, and others. So that's the general idea. And again, it has those four main components. I'm going to focus mainly on I'm not going to talk about the feature store because we don't have a lot of time. So I'm going to focus on the other components. But if you want to look, go into MLRun.org. You'll find information. There's lots of documentation with examples. You can install it on a single Docker, or you can install it on Kubernetes. But essentially, it has those four components: the feature store, which is essentially all the data engineering aspects and feature cataloging and serving and so on. It has the real-time serving pipeline, which is essentially ability to compose, all the application logic, which includes model serving, data pre-processing, post-processing, enrichment, actions, monitoring, all in a single graph. The monitoring and retraining logic, which collects information from the real time and can retrain the models, and all the integration around CI. So how does MLRun solve this problem we just mentioned? So by nature, MLRun works with serverless engines. It supports multiple serverless engines for different workloads. So it supports simple, jobs in Kubernetes for batch workloads. It supports Spark for data analytics workloads, and Dask for data analytics workloads, Horvath for deep learning workloads, distributed deep learning workloads, and Nucleo for all the real-time activities for data ingestion, serving, and so on. So those service engines, they can essentially accept a piece of code. They automatically build all the service around them, the containers. They build the containers. They deploy those containers. They control the scaling of those containers. If you have more workload, they'll essentially scale out or scale down, which is great for efficiency. You can significantly lower your cost and increase your scalability using those auto-scaling features. And another important thing about those functions, they have a sandbox. Essentially, everything that goes into those functions and goes out is recorded automatically. So you don't really need to do this parameter injection and logging and instrumentation and all that. This is done automatically for you. And you can essentially accept all those parameters and data inputs by pointers and so on, and generate all those outputs, and the serverless functions will do everything for you. So it changes the flow. Instead of the traditional flow where you write a piece of code in your Jupyter notebook or PyCharm, and then you give it to someone else to build a service for production over Kubernetes, and another guy take that service and compose sort of a pipeline on top of it, and then yet another guy builds monitoring and observability around everything. And this is a very tedious process. Using MLRun, it essentially changes everything to become much more codeless and automated. So you can write your code in your IDE with a single API call or UI call or CLI call. You can essentially turn your code into an elastic, fully monitored service. You can just take those single functions and draw them into a pipeline and launch a full pipeline that can comprise of data engineering and training and testing and deployment and so on. And all those functions, they auto instrument, they auto log and auto monitor. So you have tons of data that is being gathered automatically and analyzed automatically. You don't need to do any additional coding. And it essentially allows you to build a feedback loop of, for example, retraining data or examining production results and retuning your features, sort of a more continuous architecture. And everyone that's using it really loves it because it solves the problem of moving things to production with minimal amount of engineering and maximum scaling and lowest cost. So I'll give you just an example. How do we do the same thing we did before with all the logging and everything? So you just write your own simple function. This is a very simple standard function for training using scikit-learn. So you just pass a bunch of parameters to it, and it does some fit and split and so on, and that's a regular code. The only thing that we touched here is essentially added one line of code that registers your model. Once you added this line of code, it essentially does all those things automatically for you. So it's logging the artifacts, the matrix, it's computing data lineage, it saves all the operational data, it generates models that are production artifacts, so you can even choose the format, whether it's JSON or Onyx or Pickle or whatever. It knows how to optimize your models. It knows how to do instrumentation and profiling to your code. If you're running with GPUs, it will actually report into TensorBoard and do profiling for your code and tell you which methods, which layers are consuming more CPUs. So there are lots of operational aspects. So the data scientist doesn't need to know anything about MLOps, just needs to add one line to his code, sort of wraps his model, and that's it. And in order to record the parameters, I don't need to do any arc parsing, any command line. I'm just sort of specifying my parameters. MLRun will analyze your code and will automatically figure out that you have those parameters with those data types, those default values. If you'll add documentation strings, it will even scan your doc strings and generate documentation for your code. And then once you've saved that function, you can actually launch it from the UI and just ingest a bunch of parameters. Another thing that we discussed was the data abstraction. So instead of figuring out, do I need to have local file or a file that's in object store in S3 or in NFS or in Google Blob Store or maybe in Snowflake, etc., I could just work with an object called data item. And this is abstracting away all the aspects of data. It's also automatically recording data lineage and doing a bunch of other cool things. So I just pass this data object. I want it as a data frame, and I have a data frame. I don't really care if it's a file or a structured database or object store, etc. And again, all of that is doing this automation, single line, native code, no need to do anything for MLOps. So your data scientists can just do their stuff, and all the MLOps is done automatically for them. And how do you use that stuff? So I have this function. I want to turn this function into a microservice. So I'm just calling a single function called code to function. Take this Python file, or it also supports notebooks or other formats. Take this file and give it a name, default image, etc. Maybe some Python requirements. That's it. Now I have a microservice object, and I have this microservice object, and I can say just execute. That's it. Or if I want to execute it with parameters, I can just execute and give it data sets. And data sets could also be relative. They could be relative to a previous execution. I don't really pass data. I'm passing data objects, which are pointers. I can pass parameters. I can let it automatically build hyperparameters by just specifying, instead of specifying individual parameters, specifying arrays. And this is the most simplistic form. There's a lot more capabilities. You can do early stop. You can choose the hyperparameter scanning algorithm and so on. But because I can inject a bunch of parameter permutations and record all the results, then it's becoming really easy to run hyperparameter or AutoML on top of your code. Essentially, you're telling it, push those parameters, evaluate based on the maximum accuracy attribute. That's it. And then it also records. These are examples of the things that were recorded automatically from my code without writing a single line of code. These are the metrics. These are objects or artifacts, various, the model object in the model storage, and other things in sort of file system. How does it all work? Essentially, what MLRun does, it's a service that has a bunch of services built into it. User interface, it has sort of the main controller that you talk to, database, access control, resource management, and so on. So you can essentially call the API using the SDK or using a web API or using a REST API call from either your IDE environment or your automation tools or just from the MLRun UI. So you can just create a function, launch a function, create a pipeline, launch a pipeline, and so on. And what it does, it essentially launches those serverless functions and execute them, record them, and logs the results in the database. And has these abstractions to external data storage and also to external services. You can integrate with Azure ML, with SageMaker, with other frameworks to extend this functionality beyond those microservices that run on this Kubernetes cluster. This is all running on a Kubernetes cluster. So that's a general idea. Now, nice thing about those functions, they're not limited to batch. What you're usually doing in training in testing, data preparation is batch. You're taking a data set, you're running it into a system, and you generate the model. But the nice thing about those functions, they can actually be real time, real time, very, very fast, sub-millisecond latency. So, and you can just compose a pipeline and grow a pipeline that says, you know what, just start, meaning I want to get an event, an HTTP event or a Kafka event or any of the supported inputs, contextualize it, enrich, for example, getting a user ID, I want to get the entire set of user features. I can put an enrichment component, pre-processing, take my models that were generated in the training and build an ensemble on top of them, some post-processing, and so on. You know, we've seen users using this and building graphs with like 30 steps for NLP applications to process PDF documents, or for image processing, all sorts of image permutations, video stream processing. You can build any application you want using this technology. You can just build a bunch of built-in classes or your custom Python classes or functions and draw those graphs. And with a single line of code, you can deploy it to a fully elastic, auto-scaling, both horizontally and vertically service. So that can cut huge amount of cost, huge amount of engineering effort, and so on. And all those functions, they're also self-monitoring. So this is an example of the monitoring supported by MLRun. You could have the built-in monitoring in the MLRun user interface. Also supports Grafana for your ops teams. So you can actually go and measure everything that was running, not just the layer of CPU and memory and those metrics, but this is an example of actually seeing each model and the drift analysis per model or drift analysis per feature per model. This can actually go very, very deep into the analysis of your online activities. You can add custom metrics to measure the business ROI of your model. You could do a lot of nice functionality to monitor your online assets. So that's on that front. And it also supports native integration with different CI and Git systems. So when I'm building this batch pipeline, I can essentially trigger every time the code changes, every time I generate a new data set, snapshot of a data set from the feature store, I want to retrain my model. Or when I identified some drift, I want to retrain the model. So you can just say, I have all those 4 functions. The functions could be taken from the MLRun marketplace, which is essentially just an open source market for components that do things like data preparation, training, serving, glue logic, integration with other services. So you can build your own functions or just integrate built-in functions and compose a graph for your machine learning CI. And then you could just execute that graph on an event and track all the steps running in the graph, each individual step, what are the outputs, the artifacts, etc. These are features that you won't get from your CI. Yet this is potentially being executed by your CI system. So we're not trying to tell you go change your Jenkins or change your GitHub Actions, etc. You could just leverage them and integrate them with a system that extend them to become essentially a machine learning CI system. It's so sophisticated that it can actually go and report all the results directly into the CI system. This is auto-generated, so I can see the results of the training every time I'm changing a piece of code, running this automated flow. The reporting is going back into my CI system, so I can do governance. I can say, oh, you know what, that's a great model. Let's promote it to production. Or maybe I want to be able to go backwards, a month later and see what happened with this model that we deployed, what were the results, and so on. There's also hyperlinks that link into the full details of every execution. And there you'll see data lineage and all the more deeper logging capabilities. And the nice thing, it's not only working within MLRun, it knows how to export the data into many other frameworks, whether it's using a Jupyter widget, because the data scientist wants to see it essentially online, interactively progressing on his, where he's launching the code from, or on MLRun UI, or on all those CI systems, or TensorBoard, or Kubeflow, even Slack messages, and so on. So it's very easy to integrate it with all the other systems. And this is essentially the key message, is that you can automate a lot of the different tasks that your machine learning engineering teams are doing or data engineering teams are doing by using those set of tools, which are all open source. And there are many users that use that in production. You could see also brand names for across the board for airlines and financial institutes and so on. And just go over to MLRun. You have mlrun.org with all the documentation. You have the GitHub site, and if you like it, just give it a star. And thanks for everyone for listening in. So if you have any questions, we'd love to hear them and address them.